Vishal, I will text you the name Vishal.
Dr. Padmavati? Hello? Hello? I don't know.
Hello, can you hear me?
Yes, now I
Yeah, I just stepped out for some logistics.
yeah,
work.
okay, all right, okay. Yeah, because I'm not able to see everybody in the hall.
Hello, Comcheck, can you hear me? Hello, Professor Deshmukh, can you hear me?
Yes, I can hear you. Yes.
Okay, I was just a communications. Thank
Sure, sure. Sambudha, are you in the hall?
No, I don't think so.
Who is the local host who is recording the talk? Iser?
What's it?
Shrikant?
Vamsi,
Vaushi?
you want to come here? You may want to see.
Yeah. Yeah, Vaushi, you're still not in front of the camera.
Hello,
Yeah,
sir.
okay, now I see you. Yes. Vaushi, who else is there in the hall?
Srikanth sir is there, sir, for IT support.
Yes. And some faculty members from the IIT were to come here. Have they arrived?
I saw Arjit just now. I think they're outside having tea.
Oh, okay, all right. Because it's nearing time, so as soon as they enter the hall, we can begin. Oh, hi, Arijit.
Honest.
So, Arijit,
Hello, Professor Deshmukh.
yes, Padmavati, yes.
Can you hear me?
Yes, I certainly can. Yes.
So can we start now?
Yeah. So, who else is there? Means how are we proceeding today?
Yeah, so I will be introducing, or Dr. Arijit, any one of us can be
Yes.
introducing.
Okay. All right.
Dr. Arijit is here.
Yes.
And students are here.
So, Arijit, would you or Padmavati will introduce? Means who is it? What?
So
We are good to go. So thank you, Dr. Padmavati, and wonderful to have Dr. Shesha Raghunathan here. He's the global lead for the IBM in India, and everybody who is interested in quantum technology, of course, knows about this. So let me invite Dr. Padmavati to introduce our distinguished speaker today. Padmavati?
yeah, thank you, Professor Deshmukh. So, okay, I welcome all of you to the 15th lecture of CAMOST-G20-S20 Consortium Seminar Series. Today we have a very special guest, Dr. Shesha Raghunathan from IBM Bangalore. And so I will just give, he will be talking about embracing quantum era. Right?
Correct.
So I will just give a very brief introduction about him. So Dr. Shesha has done his PhD from University of Southern California in quantum computing. And after that, he joined IBM for last 12 years. He is in IBM in several leading positions. And right now he is in a senior research scientist position in IBM. I think he has very good lectures in NPTEL also, no? Quantum
Yes.
computing, I have seen. Yeah.
Yes.
So this is a very short introduction about Dr. Shesha, and then I will leave the floor to Dr. Shesha to talk about embracing the quantum era.
Thank you.
Thank you, Dr.
Thank you, Dr. Padmavati. Thank you, Aisar, for this opportunity, and thank you all for being here. Appreciate it. So what I'll do today is I've changed the title a little because the story that I'm telling is the title is more apt for that story, though embracing quantum era is what I'm trying to convey as a message. What I'll be doing is first, I'll give a brief overview of what quantum is at a very high level. I suspect this is a mixed audience, and certainly in YouTube, we're likely to have a mixed audience. So first, I'm going to give a little bit of a background, not in great detail, but enough so that you can move things along. And then I'll talk about where we are at this point in time, what are we doing next, and why should we care now? Those are the key messages. I'm hoping to take anywhere between 40 to 45 minutes so that you have 15 minutes at the end for more question and answers. All right, so let's get started. If the clicker works. Okay, well, this is being sorted. Let me do this. Do I have control? Huh. Yeah. Okay, can you minimize this? Maybe the control is not here. Okay. Okay, the goal or the mission for IBM is there are two missions insofar as quantum goes. One is to build useful quantum computing, This will come up in multiple places along the talk, so don't worry about what that means now. The next is to make the world quantum safe. This is again related to quantum. So we want to make sure that there is no bad actors who can do bad things for us. Today's talk is about the former, focusing on quantum computing, and I will not be touching on the latter. That's a separate topic. Okay, so let me now go to why quantum. So on our planet, we have made a lot of progress in the last many decades. It has come to play. We have made a lot of sophisticated computations. We have made a lot of automations. We are doing a lot more things efficiently. However, there are still many, many challenging problems that we have, computationally speaking. So if you look at agriculture, or if you look at industry, or financial sector, or more timely, which is more deeper medical health related applications, there are many, many challenging problems. Here are some examples. So fertilizers in agriculture, this is one key ingredient, obviously, in fertilizer. To improve the quality of the fertilizers, to make it more energy neutral, to make it more efficient, we need to understand a lot more about what fertilizers does, and what nitrogen fixation is, how does it work. It's still a little vague on our part in understanding the chemistry of things. That's a challenging problem. The other side is the industrial side. We know that the growth that we have had has led to a lot of significant carbon emissions. We want to be able to handle it, manage it, all the carbon dioxide emissions. That requires us to understand how to capture carbon. That again comes us to trying to understand what the chemistry of it, what is the interaction, things like. We don't quite understand it at a deeper level, how that works, and what is the best means or efficient way to capture carbon, for example, is. On the financial side, stability of the market is a very challenging thing. We would want to see stability in the financial market. And all of those problems invariably involves very significant amount of optimization problems, which are very hard to do today, or at least you cannot calculate a lot of this exactly. So invariably, you will have to do approximations. Finally, as you saw in pandemic time, figuring out if there is a health related issue, figuring out a drug is a challenging problem. It's not very easy because you need to understand the protein interactions at a deeper level, at a molecular level. We do not have that kind of resolution in terms of compute right now. You'll have to make do with mean field theories to figure things out. That can take you only so far, not beyond, which means that still there are a lot of things that you have to do in actual labs, figure things out, and then get the drugs to market. So there is a lot of initial cost of getting to finding the right drugs or finding the right interactions. That's a challenging problem too. And these don't necessarily have ready-made solutions that we have. Even if you throw the best machines at it, still these are computationally challenging problems. What is interesting at this point in time is that we seem to be at a point where, computationally speaking, technology are breaking. And this is a very interesting space because thus far, all the technologies that we have had, be it CPU, GPU, MPUs, call what may, fundamental underlying thrust of it was classical physics in the form of a transistor that we decide in the form of Boolean logic and Boolean algebra. And that was driving all of the calculations that we were doing. Here now with quantum, it's a break from that mode of calculations. Now we are doing calculations at a fundamentally level differently. And if you want to see that, so you had the very fundamental element in classical compute is a bit, which, as you know, takes two states, either 0 or a 1. It's a switch. In quantum, of course, it's not so. You can be in a combination therein in a probabilistic sense. And the rules of the game are different. In classical, you follow Boolean algebra in all your calculations and implementation. In quantum computing, the rules of the game is linear algebra that is set by quantum physics. And the game and the rules that it has to follow for computation comes from linear algebra. And therefore, all the shebang of linear algebra consequences of quantum physics is thrown at it. So it means that now the compute model needs to change at a fundamental level. And that's why I call it as a break from compute in terms of what we traditionally are seeing and what this model is. It's a fundamentally new model of compute at a very basic level. In classical, though the number of bits, if you had n, the total states it can go to is 2 power n, but at any given point in time, if you take a snapshot, it will be one of the 2 power n states. But in quantum, you can possibly be in all these states. And that's a fundamental difference there. The other part, so that also tells you another things. At a very basic level, the calculation in classical is deterministic. At any given point in time, though the possibilities could be infinite, at any point in time when you're exercising some data and running something, at every given point, the logic takes a specific value, either 0 or a 1. Right? It's always deterministic. Quantum is fundamentally probabilistic at the very basic level. Right? These are very, very fundamentally different models of compute. Right? So classical follows von Neumann architecture. Quantum does not follow von Neumann architecture. So it's a different model of compute. The key, there are many, many things to discuss in quantum, but the key aspect from a computational standpoint is that the state space grows exponentially as you increase the number of qubits. So this is a fundamentally exponential system. So you have this 2 power n state space to play with. The game in quantum algorithms is how do I leverage this state space that I have as much as I can and do the transformation in this exponential state space so that it solves the problem of interest. You may have been aware of 2 important discoveries, which is Shor's algorithm and Grover's, invariably leverages this state space at some fundamental level. It has to use this state space. That's the resource that you have at your disposal. In order for you to use this state space, you need to deal with entangled states, you need to deal with superposition, all the other things that come with quantum physics. It's also there. But computationally speaking, it's the state space that allows you to do these calculations. Right? So that's what is the key resource here from our computational standpoint. And that's the value. And in this cartoon, you will see a few things. The white oval are the computations that we can do efficiently today. Right? And the light blue are the ones that we struggle. And the struggling could be because the time it takes to compute or the amount of data you need to see. Right? Both are hard. If it's exponential in both sides, you're going to struggle. That's the nature of it. Dark blue is the space that quantum opens up. It's a different complexity class, and that's very fundamentally different from what we have in classical. What is important to observe is that the dark blue does not cover the whole of light blue. Do note that it's important to understand it solves certain problems. It's known to solve certain problems, at least theoretically, but it's not that it's going to solve all your NP problems, right? But then this is moving the needle in the right direction because earlier you were stuck with this blue oval. Now it's expanding that, right? You're going beyond what is doable with your classical hardware, right? And that's fundamentally new. And this space is sort of, frontier is always expanding because this is an open area of research, right? We don't know what else it can do, which is an interesting side. The application of it, 3 broad domains of applications of quantum, at least category wise. One is quantum simulation, the other is artificial intelligence, and the third is optimization and / Monte Carlo type problems. There are some known results there that can add value. Simulation is the origin story of this model. This was what was proposed by Feynman in 1981-82 when he said, can we simulate quantum physics using quantum physics? And the idea was the compute would be built on quantum physics principles. And can I simulate any other quantum physics phenomenon using this model, which is fundamentally rules of the game, as I said, follows quantum physics. So in another sense, you're simulating something quantum physical using another quantum physical device, right? So that was the idea, and that's the problem class that we are talking about. And this could mean the space of material science, it could mean quantum chemistry, it could be biology, it could be so many spaces where you're dealing at molecular level, where you want to understand what is happening at molecular level. And some of the examples that I cited before invariably involved things that you need to understand at molecular level. And if you have to do that, you need to be able to simulate those interactions of these molecules, which are at that level will be quantum physical. Therefore, we need to be able to understand, in order for us to truly understand it, we should be able to simulate it, and we need quantum computer to do those kind of simulations. That's the class of problems that the simulation addresses, and it's a very broad area in itself. The second class is machine learning or artificial intelligence. Many of you who have done any machine learning course, invariably you will know that machine learning involves some of these usual things, matrices. What is the covariance? What is the probability? So invariably it involves linear algebra at some point. It comes down to, the math of it comes down to linear algebra calculations. And as I said, quantum physics, the math of it is again linear algebra, there is an overlap there. And therefore, you can sort of intuitively imagine that there are some problems in AI machine learning that would map to this quantum physical thing. And if you map it smartly, maybe you can do something beyond what is doable classically. Finally, the third is the optimization. And those of you who are from computer science would recognize that optimization invariably involves, at some point, it will be a matrix again. If you have an objective function constraint and then you have all the other constraints that you need to satisfy, it is a set of linear equations, and you have linear equations, you then put that into a matrix, and you solve the matrix to solve the problem. So it again comes down to matrices that you need to deal with. And again, as I said, same as what you saw in machine learning, use the linear algebra that is prevalent in quantum. Can we use it effectively to solve the problem in optimization? And there could be various forms of all these applications. I've cited some subset of various avenues of exploration in each category. I'm sure there are more. This is by no means exhaustive, but you can see the length and breadth of the work that happens in so far as application of this goes. What is also important from IBM standpoint is we are trying to build a quantum industry. And for quantum industry, naturally, industry needs to participate. And why so? It's not purely a science game. You also are trying to solve a real world problem. And that's where industry will come in. We have about at least 20 engagements that we have with industry clients. And these are the three vectors I was telling you about in terms of the application areas. So different use case will have different combinations of applications. For example, if I'm a drug company looking at drug discovery, can pose the problem as a simulation problem. That is, you want to look at the molecule and understand the behavior of the molecule. Or you can ask it as a machine learning problem and say, if I tweak this amino acid, take this amino acid out and put this in, predict what will be the reaction of this molecule. It becomes a machine learning problem at that point in time. Because if you already have a bunch of experiments done and you have data for it, then you can treat that as a pure machine learning play. And can you solve it in a machine learning? And obviously you have classical machine learning there, but quantum perhaps can do a better job of prediction. Maybe it can reduce the false positives or false negatives, as the case may be. And maybe the quality of results are slightly different or better. Right? So it depends on the kind of problems you pose. That's why you will see that each of it will have different arcs going from each of them to different industry and multiple arcs, because it depends on how you frame the question that will determine the approach you take. So here are some examples of it. And some specific examples, Amgen, it's a drug related company. So they have the problem that they are exploring is they are looking at limited set of clinical data, and they want to see whether they can do a better prediction based on the limited data that they may have. Can quantum add value when you have smaller data and do not require huge amount of training data? Can it do a better job of modeling and prediction? Boeing is looking at optimization problems. That's their typical play. You can look at ExxonMobil looking at chemical reactions. There are petrochemical companies. Naturally, they are looking at some of those problems there. Woodside is an energy company. They are, again, a mining company, if I'm not mistaken. They are looking at machine learning, quantum machine learning in their workflow. There are a lot of predictions that happens in mining, for example. Misuzo, MUFG, Wells Fargo, all these are banks or financial institutions. Naturally, the problem that they are looking at is in the financial sector. All right, now let me go to where are we? So before I go, where are we? Let's define some baselines. How do I measure the performance of a quantum computer? It's just as important. So for example, typically in classical, you have various metrics. If you're looking at when you go do shopping for your laptop, you look at certain metrics. What is the processor? What is its RAM? What is its DRAM? What is its main memory? Whatnot. So a bunch of metrics you use. What are those metrics telling you? It's telling you about compute capacity of that hardware. If you're going to supercomputer level, there is a one metric called floating operations per second, flops. That is essentially used to tell you what is the compute capacity of a particular server. In a full supercomputer, it's gigaflops, petaflops, etaflops. That's how you measure the capacity of this. Much like that, we need some metrics to give a sense of how much is the compute capacity of the quantum hardware. And the way we do it is through three metrics. The first is scale, quality, and speed. Many a times, unfortunately, in popular media, scale is the only thing that is looked at. The number of qubits somehow substitutes for the compute capacity of a particular hardware. That need not be true all the time. In fact, most of the time is not true. However, it is an important metric. Do remember, I talked about the exponential state space, 2 power n, that n is the number of qubits. So you need n to get you the exponential state space. However, all I'm saying is that's not be all end all of it. You need more things to capture the compute capacity of it. So this is the possibility that is there. What is actually realizable is another question altogether. And that's why you need the other metrics. The second is the quality of the qubit. Obviously, if it's very noisy and if it's not really good, essentially you'll be dealing with a classical computer, right? There won't be any quantum features coming in. There won't be any of these quantum capacities that you could leverage. Finally, the speed. This is an important metric in different ways. It's measured by a metric called CLOPS, circuit layer operations per second. This is where some of the aspects of what I talked about useful quantum computing intersects at this particular point. So what this is when you have a quantum circuit, the calculations that we do in quantum computing invariably is a quantum circuit, the circuit that you have that you want to run. Because I told you that it's fundamentally probabilistic, the way calculations are done is you run it n number of times and then you get a distribution of the results. And the distribution is the answer that you have because you do not have access to the state that is actually there at the end. So all you have is the distribution. In order for you to get the distribution, you'll have to do sampling n number of times to get that distribution. The algorithms that we currently have is not just this sampling that you need to do. The kind of hybrid algorithms that we have invariably involves a lot of iterations of these algorithms that does sampling. So invariably, based on the data size in the quantum machine learning space, it could be a function of the amount of data that you have for your training. And possibly each data set could lead to a circuit that you need to go run and gather data, which means that essentially you're running these circuits millions and millions of times possibly. If you have a huge data or you're doing some big calculations, or in other words, the one that I will touch on a little later, if you're doing some error mitigation type activities, the number of calculations that you do will run significantly high. So what that means is that you run these circuits over and over and over again. You need to be very efficient about that. And the circuit operations per second, think of it as a intermediate system metric that is telling you how many circuits I can run in 1 second on a given hardware. So because the running part of it is there is a classical and that is talking to the quantum to make those runs, you run this n number of times. This loop needs to be efficient and fast, right? And this metric sort of captures it. Higher the number, the better it is, right? So this, why I say this intersects with useful is because if for you to have any practical solution or a useful calculation, there are two things that you need to remember. One is the problem relevant to some real world problem that you're solving? Second, can I solve it in a time that is acceptable? If I have a solution that takes 1 year to solve for a problem that I have acceptance of about 1 day as my limit, solving 1 year is not useful to me, right? So I need to be able to solve it in some practical time that is of usefulness. And that's where the usefulness has both these metrics, real world, and has to solve in real time. And that's where this metric sort of captures it. Higher the number, it means I can do more of the circuits per second. Invariably means I could do more and more compute in a given, think of it as 1 day, which means that I'm more practical, right? It's not like 10 power 8 days or something, right? It's something real and practical. So that's why this metric is very important. So how are we doing on those metrics? First is the scale metric. You may have seen the processor, 433 qubits. So the first time in quantum, at least, we have multiple layers of integration happening. This is very normal in classical world. So first you saw the qubit layer, then the wires, the connecting between them, they are in different layers connection. There is more vertical integration. This is very normal in classical. However, in quantum, this was not done like this before. It was all on the, think of it like a PCB. You put this qubit, connect them like that and all that. Now it's like going to the third dimension to doing those things. So it's gotten more sophisticated and it looks more and more like a classical processor. The sophistication of it is more and more like a classical processor. This is 433. By the end of the year, we will have 1000 qubits plus. And another one, which is 133 qubits, that will be a mainstay for a year or two. I'll talk about that in the roadmap. But we have gotten to some reasonable size already in terms of scale. So how are we doing on the other metrics? So if you look at the other two metrics, the quality and the circuit layer operations, the speed, quality is very important. So on the left, what you see is a metric that we call quantum volume. What it is not so important, then just think of it as higher the number, the good it is. Note that the scale is log on the y-axis. So linear on that scale means it's improving exponentially. One of the reasons why it is more interesting now for quantum is because this metric has gotten to some reasonable size now. And we feel once it crosses 10 power 3, it's going to get very interesting. So it's going to get very interesting. We are very close to 512. Another probably this year or so, we're going to cross this 1000 10 power 3 barrier. And we think once we cross that, that's going to get into very interesting space. This I'll touch on at the end, what's coming up next, but keep an eye on that. That metric gives us what. So I talked to you about this exponential state space. One intuitive way of thinking about it is how much of this exponential state space is really accessible to us in an efficient manner. That's what this is all about, right? Higher the number, ideally you want 2 power n. We are not there, but higher the number, it means that I have more and more access to this state space. Higher the raise, it is better for me. CLOPS, I talked about the circuit layer operations per second. Hopefully that exposition I gave just prior would bring clarity into why that number should be big. I want to be able to run this very, very efficiently. Think of how the CPU accesses your RAM so efficiently, right? Within 2 cycles, if you have to get the data back from the RAM for you to do things efficiently, right? Much like that, you need very, very rapidly so that you can do all these calculations very fast. So this has, as you can see, increased significantly in the last year. This starts from 21 to 22. Within a year, it's bumped, and it's going to increase. There will be a lot more of architectural changes to make it more and more higher. This one is very important and interesting to understand. While all of this is happening, what is happening to the adoption is just as important that we have good adoption of this quantum computer. What you're seeing on the x-axis is time starting 2016. May 2016, when we put the machine on cloud, y-axis is the number of people accessing. You will see the hardware runs and then the number of users. This is plotting the number of hardware runs on the quantum computer starting 2016. What you're seeing is we are currently in 2018 going to 2019, 2020, so forth. And that's the number of hardware runs being run, 290 billion, 490 billion, right? So you will see that these are the, all these things that you're seeing is the runs being made from this. So if you do this, you will clearly see where the lot of action is happening in terms of quantum computing goes. India is not far behind either, but there is still a lot of opportunity in terms of doing work here, and a lot more things could be done to catch up with the world. But what you're seeing is this is as of last year, July 2022, we are averaging 2.1 trillion runs. This is data from the IBM systems. Export control. Right. So this, yeah, so I should have clarified. This is runs made on IBM machines. by people. So we were the first one to put this machine on cloud, if you don't know, in 2016. And subsequently, the idea initially actually was that it was more for educational point of view. It was put out so that it was very simple, so 5-qubit machine. You had this schematic type thing where you can do drag and drop and run things and such. Initially, the idea was we wanted people to play with it, particularly students, to learn quantum computing and also quantum physics, learn how it works in real terms. And then the subsequent year, we had a Python package called Qiskit that we put out. And once we did that, it just became, had a life of its own. And you'll see why. There are over 2,100 research papers written on top of this platform. That's why you saw the exponential increase. The reason is what was initially thought of as an educational platform, it became a platform for research. And what has happened is that using that, this is just on IBM platform, and IBM is pretty much the major platform that anyone in this field uses invariably. There are other platforms too, but from on IBM platform, 2,100 plus papers have been written, research papers using IBM Quantum as the baseline platform to make those runs. Right? It's become a platform for research. And anything in quantum computing, particularly practical quantum computing, invariably these days require some runs being made on hardware to validate whatever you're claiming. That's become a norm now, more and more so now. If you look at the adoption, Qiskit is the SDK I was telling about, software development kit. You had the hardware, you need the software to be able to talk to the hardware. The Qiskit is that. You will see that there are about, if you have not seen, IBM has extensive collection of learning material in quantum, a significant amount of material. We probably are by far the biggest producer of educational material for quantum computing goes. And we have a lot of programs as well. You will see that 6+ million people have used our educational materials. What is interesting is quantum computing courses, the number of courses. Now, what has happened is that, so Padmavati mentioned about the NPTEL course, right? So that's one example of it, where we taught quantum. This was in collaboration with IIT Madras. And what we had people do is to do programming using Qiskit while you learn quantum. Right? Much like that, there are 490 plus, and I'm sure we are undercounting here because some of it we may not even know. 490 courses using quantum computing. Traditionally, quantum information science has been around since at least 90s in most of the physics departments, and more so since the start of this century. But it was more from a physics standpoint. It was more quantum information than quantum computing. That was the emphasis. I think right now what has happened with, particularly after we put the machine on cloud and all the programming platform has come in, it's also an algorithmic research. There was algorithms before, like how Shor's did, etc. in 90s, but they were physicists doing it in a physicsy way. They were not computer scientists doing it in a computer sciencey way. It's a different perspective. Now it's gotten slightly different in terms of the perspective. Now it's become more interdisciplinary, where you have different perspectives coming at it, especially the modern algorithms, which is hybrid, which borrows a lot from machine learning type modeling of the algorithmic development. So you're seeing increasingly a lot more people with those kind of background coming into play in the algorithmic research, which is very interesting in how it's evolving and developing. I think this one is basically the various our academic engagement that we have. We have what is called as quantum innovation centers. IIT Madras is one in India, currently the only one at this point in time. Hopefully, in times to come, more and more institutes like I said, Tirupati and others start getting into this more seriously and start playing with this. It's a very active area of research. And these are some of the worldwide. We have about 35 worldwide. And IIT Madras in India is the only one at this point. The other important thing that we are doing as IBM is technical working groups with 4 important areas of deep research using quantum. One is finance, naturally. Wall Street always cares about any new technology anywhere in the world. So that financial problems, you have people coming from that background thinking about quantum computing, how what kind of problems to solve. You have high performance HPC people. Naturally, there is an intersection there. Thinking about HPC workloads and say how quantum intersects that workload. Then you have high energy physics. We have CERN in Switzerland is a quantum innovation center. They do a lot of work on quantum computing. They look at various high energy physics related problems and use quantum computer to do the research. They are there, and there are many other high energy physics people trying to understand what kind of problems. These are working groups, so their goal is to bring the problem, try to solve the problem, and understand where the hardware is, what kind of algorithms are there, can we tweak the problem, what are the other interesting problems go look at. So that's the high energy. And then healthcare is another important, where quantum we feel will play a big role. And I cited one example, which is drug discovery before. So there is a working group for that, which works with IBM Quantum to explore these domains. So what I covered is where we are, both from the hardware side and also in terms of adoption, where ecosystem is, right? Hopefully I covered both those parts. Now what's next? What's coming ahead? What's the road ahead? Since 2019, IBM has been putting out the roadmap of what's coming next. Here, in this roadmap, the way you would want to read is this lowest layer is the hardware layer. These are the processors. And then the layers above is the software stack. Right? The Qiskit covers these layers. The quantum information science kit, or Qiskit, is this application or the software layer. So on the hardware side, you will see that we have 433 qubits online right now. If you have, by the way, if you have not been playing with these things, do go to quantum-computing.ibm.com. You can create and log in for free, and you can run some programs on quantum hardware and see how it goes, right? There are a lot of materials there as well. Okay, so we have this 433 qubits online. And this year, we're going to have 1,000 plus qubits and 133 qubits coming up. By the end of the year, both of them should be there. It's on target, so hopefully we should have it. Yeah. I don't know if people in there can see. Okay. These are the processes that are coming up this year, and these are the process Flamingo and Crossbill. Again, 1,000 plus qubits, 408, and then finally 2025 we'll come up with 4,000 plus qubit. What you are seeing here is that we are doing some key canonical experiments, just for your awareness what this is about. We are trying to address the scalability problem in the hardware. How do I increase the number of qubits in this platform? So these are some key canonical experiments. This is connection, classical connection between them. A crossbill is when you have two of these processes abutted to one another, and this is a quantum communication between the two. This is quantum connection, and that's the abutted nature of this one. Flamingo is a quantum communication between these processors, right? And finally, Kookaburra is a combination of all these things put together, right? So why is that important? We have what is called as a super fridge, the huge fridge, where we plan to stack these qubit processors at different levels. So naturally, you can stack them up horizontally. That's the abutted mode. And then you can stack them vertically. If you stack them vertically, you need to be able to communicate them to increase the number of qubits. And that's why this quantum communication part will become handy. So that is communication within the fridge. And once you stack them up, then what you would need to do is you will want to communicate across the fridge as well. Think of it as a sort of an intranet type thing. That's another technical challenge that's not covered in Kookaburra. Kookaburra still is looking at within the fridge part, but there will be coupling needed from one fridge to the other so that you can expand on the number of qubits, right? These are very key canonical experiments solving some key technological problems. Because again, noise is an important element. You need to be at some reasonable regime for you to get some throughput and performance. So figuring it out, and this operating at the temperature it does, you need to figure out a lot more of that. No, not in Kookaburra, but possibly even further down. Kubura may still be in the same fridge. Our view is still little vague at this point in time. However, there is a paper I'll refer you to which discusses some aspects of it, because unless you get into it, you'll never know the problem. Right now, it's speculation because we do not have multiple fridges talking at this point in time, because our goal is get the internal. So first coupling is internal, which is a one order of less complexity compared to the external thing. So we are there at this point in time. We do recognize that will be another big challenge coming up. Hope is that whatever we learn here will translate there also. So that's where we are. So that's the level of answer I can give there. All right. So these layers, I'm going to go cover these two layers, which is where IBM is likely to play a role. The role that is the layer just above the processor and the layer beyond that. So that's where it's going to be very important from IBM standpoint. So let me start with the first layer. So this is the error suppression and mitigation layer. That's part of it is, if some of you have used it, you will see that error suppression mitigation is already percolating into Qiskit already, but more will come in times to come. You'll see that in the roadmap as the next thing. So what is the idea? So the error suppression is that can you do things so that the error is mitigated? So note that while the quality of the qubit is improving exponentially, we are not still at what we call as a fault tolerant regime. In fact, we are an order of 2 away from it. So the challenge for us is the calculations that we do, can we get the maximum out of the quantum hardware, extract as much of compute out of this hardware as possible. And that is done through these error correction, not correction, rather suppression and mitigation techniques. Okay, so suppression. The idea is there could be aspects, you don't touch the logic of the circuit. So let's say this was the given circuit that you're trying to run. There are different techniques which you can do to improve the overall quality of your answer. So for example, let's say a qubit happens, one gate happens here, and there is a long time after the next gate happens because there are other qubits that are doing something, and then this qubit comes and you do some action later. Then the qubit standing still could degenerate, right? This idea as such is a very old idea. Spin echo, if some of you are from the earlier thing, is basically what you do is keep pinging at it so that it remains in that state and not degenerate. So there is a technique called dynamic decoupling that does that, where basically you are doing multiple of these gates which cancel each other out logically. So you're not changing the logic, but you're doing it so that the state of the system remains at the place that we are, and we do not lose the state of that we have, right? There are similar ideas in terms of doing different calculations at pulse level to get better answers and so forth. So all those things fall under error suppression technique. You are trying to suppress the error. The other is the mitigation part. In the mitigation, what you do is you change the logic a little. The idea is very interesting in some sense. So think of mitigation as an intuition is, think of it as noise cancellation headphones that you have. What do you do in noise cancellation? You have noise in the ecosystem. The way you cancel it is throw noise at the noise to cancel them out so that you don't hear anything. So this approach, the idea is you sort of profile the qubit or characterize the qubit, understand the noise profile of it, and probabilistically apply gates, imagining that there will be such a noise on those gates or on those qubits, and on average, it will cancel out the overall noise that you had. Individually, the circuit will not cancel, but on average, when you take an ensemble average, it will cancel out. Okay, so that's the probabilistic error cancellation. You probabilistically apply. If there was a noise, you could imagine there was an additional gate that the environment performed on the gate, right? So if you probabilistically, you did the right probabilistic calculation, you would have applied a counter gate, assuming that there was a noise, and you would on ensemble average would have gotten it right. And therefore on ensemble, you would have gotten the right answer. That's where this was an important paper a couple of years back, which basically showed theoretically that you could get zero bias estimation of any operator. Technical speak, but basically it's telling you that it gives you the answer without bias. However, it comes with a cost. The cost is the number of circuit that you need to execute. Because now the question will be, where will I add this random cancellation gates? There are exponential spaces where you can add, right? So naturally, the number of circuits that you can possibly do is exponential. If the noise is at some reasonable level, as the noise reduces, the size of the exponential also reduces because your probabilistic distribution goes that way, and it becomes more manageable. So if you see, that's why you see all these circuits in parallel, because you are doing this probabilistic potential cancellations operations there, and that can be exponential. That's a challenge. And that's why, connecting to the CLOPS argument that I was making, even if I had higher CLOPS, if I could run things very efficiently, I could do more of these calculations. If I was limited by that calculation, that is the loop of running things efficiently, then I'll be limited to what I could do with this technique. I could do only certain amount and not beyond. So again, all of this is working towards this useful computation. Now let's go to the next layer. The next layer is the quantum serverless. Now, the lowest layer was about running things efficiently, each circuit, running it efficiently, sampling it, get the results back, and so forth. If you go one layer up, you have what is called as the quantum serverless. You go into the level of a cloud. So you have your workload deployed in cloud and running these quantum runs. So it could be that you have a hybrid algorithm, classical quantum algorithm, or any other workload where some portion is quantum, think of it that way. That is running in some cloud. Now you need to be able to manage these things. That's what we mean by serverless. Serverless is essentially this, think of them as Kubernetes type thing, which is deployed on the cloud. So intelligent orchestration is about, you may need different kinds of resources. It could be a CPU, GPU. The number of CPUs could be different because there is a classical portion that you're running, and then there is a quantum portion that is running. So you need to do orchestration there. And then you need to have the circuit knitting and cutting libraries. I'll touch on that in a bit. So I'll talk about this a little bit. Okay, so thus far what I had explained is you have the hardware at the bottom, and then you have a Qiskit, which is here, and then you have the software tools, workflows available on top. Having just being able to talk to this hardware is not enough if you are trying to solve a real world problem. You need to be able to take this even further, and that's where I was talking about the cloud. This one is needed. So for us to get benefit from all of this, you need to study the workload that you have. And those of you who are in computer science would recognize this more readily, particularly if you are working in HPC type problems. So typically you will have the target, the accuracy, you will have the cost, how much money, and then the time. All of this, it's a multidimensional optimization problem that you do at a higher level, and you have a workload. This is the thing that you really worry about and see what can you do to achieve the target that you're interested in with the money that you have, and within the time budget that you set, can you solve the problem? Okay, now, before I go deep, let me touch on the toolkits. So I mentioned that in order for us to solve the previous problem, that is, you have the target, you have the budget, you have the time constraint, you need certain tools at the quantum level. And that's what I'm talking about now. You will see how it fits into with the overall thing in the subsequent chart. So let's take circuit cutting. So circuit cutting, the idea there is typically you saw that 433 qubits, 1000 qubits, etc. While those are super impressive and we are really proud of it, in real world problem requires a lot more qubits typically. For example, if you are solving an optimization problem at scale, you are looking at hundreds of thousands of variables in an optimization problem. That in quantum sense could mean hundreds of thousands of qubits needed to solve a particular problem. So we are nowhere near there at this point in time. So what you can do next is that you could come up with a technique, and this is the toolkit that does some of those things. Can I take a big circuit, slice and dice them up into smaller pieces, and run each of them in those smaller process that we have today, and then stitch them up together later? All right. So that's the idea of this circuit cutting. So that's why you see one circuit, slice and dice, and then you run them separately, and then there will be a lot of those circuits that you run, and then eventually get the result. Remember, these are quantum circuit, not classical. So which means when you do this slice and dice thing, I say it very lightly, but the cost grows exponentially in terms of the number of circuits that you do, because we are breaking a quantum communication, which means that there is a cost to it. However, given the limitations that we have, you need these kind of toolkits to do this complex analysis for us to leverage the best out of the hardware that we have. Quantum embedding is another interesting idea. Is probably most relevant and useful in the space of quantum chemistry, material science, and elements where it involves quantum simulation. Typically, in that space, you have what are called as active and non-active or inactive regions. When you map out those energy landscape that you have this inactive area and active area. Active area, think of it as valence electrons interacting with other valence electrons and doing all sorts of things. So maybe then the current mean field theories like density functional theory that is used to describe this, or molecular dynamics, invariably doesn't describe all the interactions very well. And that's the limitation of classical hardware, because it can't grow exponentially. So the idea is quantum is not big enough to solve real world molecular problems, because number of molecules, the size of the molecules could run into thousands. We do not have that right now. What you could do instead is embed quantum portion into the density functional theory. For example, look at the active part, which is the relevant part where the interaction matters, describe that using quantum mechanically and run it in quantum system, while the remaining portions run it classically using your traditional density functional theory. And that is called as the embedding part. So this is an interesting and important idea, I think. How relevant and useful it will be, we'll get to see in times to come. But this was demonstrated with some specific examples. Entanglement forging is a similar idea where you're again slicing and dicing, but doing it slightly differently. And trying to, again, you will see from individual thing, you will get into a summation. Invariably, that's what happens. You'll have to do a lot more of these runs and gather this. So in this case, they did this classical forging, as they call it. They took the water molecule, I think it required 10 qubits or something. They did the simulation using 5 qubits, multiple of those runs, and stitched them together classically to get what would have happened if you had 10 qubits and run it. Right? So you're using less number of qubits to do a bigger calculation, but the cost is you will have to do a lot more of these calculations. But that's the kind of toolkits you need. As you scale the problem up, you need these kind of toolkits available for you to be able to combine different ideas together, mix and match, and see what is useful and relevant. So now back to the big picture. So when you saw this accuracy, cost, and time, the key part is to decompose the problem. And that's what the previous chart I was telling you about, decomposing the problem. So I talked about that as more as a toolkit leading into this particular problem, which is how do you decompose the workload into CPU, GPU, and QPU, or quantum processing unit. So again, the trade-off is accuracy and cost. The more run that you need to make in quantum costs you more, but it gives you more accuracy. Then you go into the orchestration layer. You identify what you run in quantum. After that, you now need to figure out what you want to run classically. You have CPUs, GPUs, and whatnot. How do you move the workload around? Again, there in the classical space, you're looking at cost versus time. The more the money, you can buy more CPUs and GPUs. You can run more things in parallel, and you have to orchestrate all of those workloads. You kick off some runs here, you kick off some runs there, pull them all together. Orchestration, that's what Kubernetes does. That's what cloud does typically, and your workflow will be deployed in cloud like this. And then you have the lowest layer. Once you identified what runs in quantum, goes to the lowest layer, the Qiskit runtime. That's the layer immediately above the hardware that I was telling you about, where error suppression and mitigation is. So that's what this one is. Again, you will have a trade-off accuracy in this thing, because I told you that Mitigation costs you more because you have to run a lot more of these circuits. If you don't have money or don't need that accuracy, you don't need to run those kind of calculations. You could run less accurate or coarser runs if that satisfies your requirements. So again, it's a target dollar, and you have your time constraint. So again, the trade-off, again, there are a lot of trade-offs involved at the lowest level of the API as well. So putting them all together is what we call as for quantum. So that once you have this, now you have a full picture of how will you deploy a workload, a real world workload at scale. From the left, you can take the laptop away and it could be another server which is running your actual workflow. Then you have the overall platform to be able to do a more sophisticated quantum calculations. Doing quantum calculations requires you some CPUs and GPUs as well, because you need to do stitching of these answers in classical. So that's why you need some of these platforms to make it happen. All right, why now? So this is the last section. Hopefully by now I've told you what quantum is, where we are, what's next, and why now. Okay, so now why now portion, I want to highlight this challenge coming up next year, 100 by 100. The idea is that next year, starting next year, we will have machines that can run 100 qubits with depth of 100. By depth, each is a 2-qubit operation is considered one depth. So you could have 100 of those. So that's what this one is showing, right? 100 of this. This circuit you will be able to run in a quantum hardware in an unbiased fashion. So remember the probabilistic error cancellation, the mitigation technique I talked to you about. You could run this kind of calculations with this kind of circuit in a hardware and get an unbiased result from this. That's what we have in our roadmap. Starting next year, you will be able to start making these kind of runs. As the year progresses, I'm sure we're going to do a lot more of versioning of this, and more better results will come through the year. But that's what we are at. For those of you who are quantum aware, quantum computing aware, this is highly non-trivial. We are getting into a regime where usually, if you have done any quantum computing, the question, if somebody asks, how many qubits can I simulate efficiently in classical, in a general form, it will be anywhere between the 50 to 60 qubits is where it lands. The best is 55, 56 or something on those lines. Only point problems of specific nature, you could go a lot more, but a general problem pretty much saturates at 55 to 60. The reason is you need memory of size 2 power 55 to manage. It's just ridiculous, right? You are dealing, so 2 power 30 is giga, 2 power 40 is peta, and then you are going to eta level. 2 power 55 is like super eta level. That's just impractical. It's just not going to happen. So even if it goes to 65, 100 is still way off, right? And that's why we think we are entering a regime of the unknown, of what the problem can be solved. It's getting into a regime where classical will find it harder. It doesn't mean the problem that we run can't be solved classically. We don't know. Human ingenuity can find things out. But in general terms, we are getting into a regime where answers are going to be unknown. The regime is, what it can do is an unknown space. And that's where it's exciting and interesting, in that what problem can leverage this and possibly demonstrate that you could do something only quantum mechanically or quantum computing and not in classical. We don't know what that is, and that's an open problem, right? So that's that. So why that is so? I'll give you a quick rundown of this. So the way you'd want to do is, this is the depth, this is the width. Width is the number of qubits, depth is how deep the circuit is. The more the deeper the circuit, the harder it is. Noise starts prevailing. So it's always challenging. So we had a paper, I'll touch on it just now, in Nature, the cover of Nature, a month and a half or 2 months back, that you ran 127 qubit with 60 depth. That was a very important result. We could go wider, but less deeper. We have some results there as well. What we are doing is we are doing the both, which is where the interesting space comes for us, right? 60 is still within the reasonable ballpark of classical. I told you about 50, 55 being the kind of regime that classical can do. So 100 is, to us at least, it's actually well beyond. So it gets to a regime or kind of space that is going to be open, and we don't know what we're going to get at this point. So why it is important, and again, this is an illustrative chart. Why this is important is we feel we are getting closer and closer to this. On the x-axis is the circuit complexity. As the quantum circuit complexity increases, classical resources required grows exponentially. We know that already. Quantum error correction is the standard technique to manage it. Its resources grows, we know that linearly, but then the initial cost, the gap, the simulation cost is very high. And this will happen at much later because it requires certain threshold of error. We are not there. But then the question is, can we do something valuable now, today, or within near term that can give you some what we call as quantum value? That is, you're doing some calculation well and truly beyond classical. So we feel we are getting closer and closer to this point where it's going to tip over onto the other side, which is beyond classical. Right? And that's what we want to get there, demonstrably so. That is, you want to solve a real world problem at scale in a practical time. That's what I defined as useful quantum computing is. We want to get there and solve and demonstrably show that this problem cannot be solved classically. And that eventually, after few iterations of counter, somebody will come up with quantum inspired, somebody is going to come up with something else. There is always something that will happen back and forth to figure out, can we do this efficiently classically if I had a different approximation perhaps, a different technique perhaps, and so forth. But at some point, there will be a distance that will not be managed. And that point is where we get into quantum advantage. However, once we start demonstrating these kind of results, then we start unlocking quantum value. You are unlocking the value of the quantum hardware. And then you will have some industry and business around it. So this is the work that I talked about. This came in the cover of Nature. For those of you who don't know, Nature is the premium scientific magazine that is there. This was the cover in June, I believe, of Nature. Do go give it a read. This we call as quantum utility. So what was done was particular standard Hamiltonian that's called transverse Ising model Hamiltonian. We picked that one that has a wide application across chemistry and biology and space, but the Hamiltonian is that. What was done was that we tried to simulate using quantum and then classical. Initially, we picked the smaller size of the Hamiltonian so that it could be simulated exactly, demonstrated that quantum generates the right results that you can get classically and the classical algorithm work. And you started increasing the dial of complexity. And when you started increasing the dial of the complexity, exact solutions at some point started diverging. Then classical had to go into the approximate solution. And later, they had to go into neural network type solutions. Again, it's a machine learning based solution. That's the best that it can do. And keep dialing up in terms of the scale of entanglement that is needed. You keep dialing it up. Then what happens is at some point, classical and quantum just diverge. Just what classical cannot. And what this shows, at least what we think, is that quantum is demonstrating utility. That is, we are able to solve something that classical cannot. We are not claiming advantage just yet. As I told you, there will be back and forth, back and forth. And secondly, for advantage, we do need a real world problem. This is an abstract Hamiltonian. It is not a specific Hamiltonian solving a specific problem yet. So we need to get to the specific problem, a real world problem at scale, and demonstrate this and show that classical cannot. Even after others will come up with other way of to demonstrate you could do it classically. After a while of this back and forth, at some point, it becomes demonstrable that classical cannot catch up. At that point is where we get into quantum advantage. But this is an important result, and no wonder it showed up on the cover of Nature. It's very important, demonstrating utility of quantum systems. We want to move towards quantum advantage. And to get to quantum advantage, we think it's going to be through error mitigation. We don't necessarily need error correction per se to get something valuable out of quantum computer, this is our view. This gives a continuous path for us to go from where we are to error correction, and along the way unlock the quantum value that we have. And finally, I'll quickly touch on where we are looking further down the line. This is a little bit further out, quantum-centric supercomputing. The vision is you're going to have QPUs in a data center like how you have GPUs and CPUs. I touched on some of the elements already in terms of the orchestration, other tools that are needed to manage that. This is all working towards that vision. Here, a few weeks back, IBM had an announcement, press release. If you have not seen, please do go see that we're going to build 100,000 qubit machine by 2033. It's an alliance with the University of Chicago and the University of Tokyo, doing different parts of this work. It's a 10-year, $100 million type investment that is going to happen here. So what you're seeing is a pictorial view of what it will work on. Each of this is a super fridge. You will see that there are 1, 2, 3, 4, 5, 6, 7, 8 of them in one network. And think of each network producing 25,000 qubits, 4 of them here, 100,000 qubits in all. And the processes that I described, different processors, and each of them will be communicating between them and across all of these things. That's what we are working towards. And this will happen in the next 10 years. At least that's our roadmap at this point in time. And we are putting money behind this as well. Finally, I'll leave you with this video. This is what we think eventually it will look like when you make a workload or a run here. So you are a user sitting here, you talk to the cloud, you make the run. Then the first thing is it goes and it kicks off a job. So you have your program, it goes to the server, and the server then has to do what? First, it has to do the decomposition, right? So it's going to go compile the circuit. It's going to show you the circuit. So in this example, I think this is the circuit, let's say, and this was this big circuit, parameterized circuit. And let's say the decomposing, let's say in this example, it shows that it's going to be divided into 4. So that's what the circuit cutting and knitting techniques that I was telling you about. So that's what happens. Then it then sends to the backend Qiskit runtime. Then the runtime then goes and sends each of the circuits to the 4 processors here. The circuit goes in, makes the run, gets you the result back. Remember, these are very sophisticated calculations that are happening. You need to keep track of many things and do the right kind of averaging and doing the right kind of calculations. So that's why you need to have that reconstruction of it. And once you reconstruct, you get the result back. And then this goes in an iteration. If you're solving for energy of a molecule, it's not that one run that's going to solve it. You will have n number of this iteration. And there's n number of these iterations sitting in a larger workload of drug discovery, that whatever the workload that a company uses is where it's going to sit. And with that, I thank you for your attention.
Yeah. Thank you, Dr. Shesha, for your nice, detailed and up-to-date overview about quantum computing. Professor Deshmukh, do you have any comments?
No, very, very fascinating talk, and how the calibration of this technology is done at different levels and where it is going. It's very exciting to hear it. And Dr. Shesha, I want to thank you one more time because I know it has been a very hectic visit for you. You are in the thick of so many things. But let me first ask Dr. Padmavati to conduct the question answer session, maybe.
Yeah. So the floor is now open for question answers. And Dr. Oh, you have the first question. I thought you.
Yeah, so it is a fascinating talk and getting an overview of the IBM quantum ecosystem and how things are being staged for the long-term development. My question is, sometimes we hear, for instance, there are competing platforms on quantum computing, right? These competing platforms try to project their systems, like, for instance, if you take Honeywell, right? So Honeywell never tries to highlight the number of qubits, rather they highlight quantum volume, right?
Yeah.
But let's say if you take Google or IBM, they focus primarily on scaling up the number of qubits, right? So from a new user who perhaps wants to get into the game, what that person needs to understand, let's say if he or she is interested in developing a quantum hardware, should he or she focus more on the volume aspect, or just simply go by the logic of scaling up the qubits?
It's not yes or no answer in this. The reason is that at this point, there is no one clear winner. Like say in classical, you had your transistor technology, what eventually became CMOS, but initially it was an NP transistor, which sort of provided a clear path to an advantage. And other technologies, it sort of beat the other technologies in all accounts. I don't think we have that kind of a technology in quantum just yet. Each technology comes with a trade-off. Each technology comes with certain advantages and disadvantages. The question is, right now, obviously, IBM and Google are betting on this one technology. There are others who are betting on the other technology, and that's good for the overall ecosystem. We don't know which one will win eventually. We do think, I mean, as IBM, we do believe superconducting is the right technology for us. There are many reasons for it. One is it's built on top of classical hardware fabrication, silicon-based fabrication technologies, for which we have much good 50-60 years of experience doing it, and a lot more sophistication of doing that. We don't have to reinvent a lot of things there. Leverage existing tools and do it better. It by no means means it's not scientifically challenging. These are highly scientifically challenging things, what is being done here. Even where we are at is testament to some serious work that has happened. Having said that, so that is one. Second is that practicality is also another part. We do see the scaling problem could be addressed in some of these ways, because as I told you, number of qubits is also important. Eventually to work towards error correction, if that's where we want to go, you do need a lot of qubits to make that happen. While I do agree that quality is very important, and I highlighted specifically on it, it's a combination of it is what will take us where we want to go. While we work on quality, we also need to scale out. Both needs to happen is what we take. Thirdly, we operate in few gigahertz frequency. So what that means is that the per gate operation costs us in terms of 100 picoseconds or something in the order of 100, 200 picosecond, give or take. 2 qubit probably costs us more. What that means is that in real time, in 1 second, I can do possibly a very deep circuit. If my per gate time was in the order of milliseconds in some of the other technologies, that is the case. If I have to do a similar calculation, it may run into few days. Okay, so what that tells me is that from practical standpoint, for real world problems which are super complicated, we do need this per gate time becomes important as well. And we'll need to keep an eye on that. Can we do that effectively, efficiently? And that's where the other system related CLOPs and other things come into play, so that we really get everything that we can get out of it. But if I do just a back of the envelope calculation, if the per gate cost is in the order of few milliseconds, and my per gate is in the order of few picoseconds, hundreds of picoseconds, you see orders of difference. So that makes practical difference. When I solve real world at scale, whether can that scale out to a different thing is a question. So again, open problems, we don't know which one will win. We do think this is a better technology with the right kind of mix at this point in time, for which we are betting on, and we are betting serious money behind it.
Right, thank you.
Any further question? Anybody?
Hey, hello. What I am thinking, maybe this is a naive question. So can there any problem that we can solve classically very well, but not quantum mechanically or by quantum computing?
Well, yes and no. if I want to answer it from a computational complexity, answer is no, because P is contained in BQP. So computationally speaking, BQP always, so P is contained in BQP, BQP is not contained in P. It can't go the other way. So which means that BQP, which is the computational complexity class for quantum, is over and above what is doable in classical, even probabilistic classical. Okay. So the answer is no formally from a computational complexity argument, the theoretical argument. Practically though, yes, classical hardware has had good 60 years head start. For example, if you want to do a multiplication, A star B, right now, you may do it with in the order of few microseconds in classical. It may take about, I don't know, 30 cycles of classical compute. I mean, 30 or 40, which means it's under a few 100 nanoseconds or so. You'll be able to solve a multiplication problem. If you want to do the same in quantum, it may take many seconds to solve it today. Right? So in practice, that's one. Second, there is an idea of quantum RAM, but in practice, we don't have memory in quantum. So if you are dealing with memory transactions, say you are doing a bank transaction, you're transferring some money from A to B, that goes to the backend to a bank, and the bank then has to write that into a database. IBM produces a processor that is 5 gigahertz plus. That's a Z processor. That sort of is a key backbone to all the financial transactions that we do. That is the per cost of the transaction is in the order of few picoseconds to write to the database. That's the task. In quantum, you can't do that kind of efficiency right now. So for a long while, we're going to stay with classical.
Thank you.
Actually, I had a question. Yeah, later you can answer. So this is, can I ask you to elaborate this quantum volume a little bit more?
So the idea of quantum volume is that, so it's like a square. Think of it as a square. That is, let's imagine I have 5 qubits with depth 5, because that's the circuit that I want to run. Can I run it in the hardware with a probability of success greater than, I believe, 66 point some number, some 2/3, more than 2/3 of the time, some number. And if I get the efficiency of more than that, that's the kind of run that I can make on that hardware efficiently. Okay. So in this case, the volume then would be, in the example I cited, it was 5 qubits. So the quantum volume would be 2 power 5. Okay. If I go for 6 and you can do the 6 depth, it's 2 power 6. So it's like ever expanding square, if you will.
Okay, thank you. Any further question? Okay, can you check if there are questions from online participants? No? YouTube? YouTube you have? Okay. Okay, in that case, let us all thank Dr. Shesha once again for this wonderful talk. Professor Deshmukh?
Yeah, thank you very much. This has been a very wonderful talk. So thank you, Dr. Shesha, and thanks to everybody over there for making this such a powerful event. Thank you all very much.
Thank you.
Thank you, Professor Deshmukh. Yeah, thank you all. Okay. Have a nice weekend.
Yeah, and have a safe trip back, Shesha. Thanks for the troubles you have taken today. Have a good trip back.
Okay, Professor Deshmukh, we are closing the session. Yeah. Nobody in YouTube, right? No question.